Thank you, Martin, for the introduction, and thanks to the organizer for giving me this opportunity to be here, which people who know me know that it is always a pleasure for me to be in Vienna. I also lived for a while in Austria, but not here. I was in Linz, way smaller city, and every time I had occasion to move to Vienna, it was like meeting the world, because it's going from the country to the big city. And so this is full of good remembering for me coming to Vienna. I want to speak to you about this joint work with my colleagues in Naples, Giovanni Scilla and Bianca Strofolini, and this is variational calculus. I must be honest, this is hard-boiled variational calculus. I took the occasion because sometimes you have to speak about theoretical stuff, so I already apologize, there are no pictures. This is boring mathematics, but I will do my best to keep the attention as high as I can. And definitely we are going to speak about singularities because there will be fracture, but we will be focusing also on bulk energies and on the role that the interplay between discontinuities and bulk energy may have when you assume a variable growth, as we are doing. So there is P of X here as for a growth. And the talk is about integral representation, and people not acquainted to gamma convergence may be wondering what integral representation is. So let's be starting by speaking about this. So what's an integral representation result? It's something very theoretical because you have a functional, you give some hypothesis on the structure of this functional or some space of a measurable function whatsoever, and you say if some requirements are met, then you can say that this functional is the coupling of two integral terms. And in my talk, we will be interested in one integral term on the bulk, on the reference configuration B, and some term which is concentrated on some submanifold, or, to be honest, rectifiable subset. And the question is, why do you need this? Don't you already know that your functional is an integral one? Yes, if you are given a concrete one. But when you are doing relaxation, or when you have many functionals that gamma converge, so when you want to do homogenization, for instance, this is a typical application, during this procedure, you may not know anymore if your functional still admits such a representation, and you want to show that actually such a representation is available, and also give some formulas to compute the energy densities. And this approach is very well consolidated. So there is a short literature about integral representation results on different settings on different functional spaces, obviously starting from a Sobolev setting, but then meeting the requirements of BV functions, SBV functions, and also special functions of bounded deformation, which luckily enough, we will not be dealing with in this talk. And there is also a result for Sobolev space with variable growth by Koch and Mucci. I will be speaking about that during this talk. So this is why, very shortly, we will be needing an integral representation result, which I will illustrate. And the other question is, why do you want to deal with a variable exponent setting? In some sense, this is a natural requirement if you postulate that you are in a heterogeneous setting. So we have some material which can be, for instance, elastic, which has a stored energy, and typically the stored energy is depending on the position in the reference configuration, on the deformation itself, and on the deformation gradient. And for some reason, we know that usually this energy has a growth, is a P growth, but okay, the principal case is P equal to 2, but there are different P that can come into play, different integrability exponents for the strain that come into play. And actually, if you have something heterogeneous, why do you have to postulate that there is a single one, a single growth exponent accounting for every point of the material? And so one way of letting heterogeneity enter in this discussion is to postulate, for instance, that the growth is driven by a variable exponent. It's not the only case. You can have mixed growth. You can have double phase functions. There is a huge literature in the Sobolev setting. Probably this is I would not say the easiest example, but it's prototypical and can be directly attacked. While when you want to deal with double phase and so on, you probably need more refined thoughts about Orlich or generalized Orlich spaces, which are not going to be illustrated in this talk. And this will be our bulk energy. This will have a variable growth. I hope you think, as I do, that this can be interesting. And the point is that this bulk energy will be coupled with a free discontinuity. So there will be a discontinuity set which is not given a priori. It's the discontinuity set of the deformation U. This may account, for instance, for cracks, for fracture, and so on. But this coupling is also going to affect the meaning that we give to our gradient, to our deformation gradient. In the Sobolev setting, deformation gradient has a distributional meaning. Is the gradient, is the distributional gradient, which is LP. When you have functions that have free discontinuities, this gradient is defined in a weaker sense. It is no more the distributional gradient. It can only be defined by some approximate differentiability or equivalently by using the Radon-Nikodym theorem. So it only exists in a measured theoretical setting, and it has no distributional meaning anymore. And this is going to affect the discussion because you cannot go directly to the result in Sobolev spaces when dealing with this energy. But we will see that when you do blow-up estimates, when you localize your functionals, in the end, this is what you do. So you would like to think of your function as a Sobolev function outside of a closed set. This is completely false. BV functions are not of this kind, but when you localize the functionals with some modification, you can go back to this situation, which is the ideal one, the one you want to deal with. And also variable exponent has attracted a lot of attention, starting from the very, very theoretical setting when one simply deals with LP spaces with variable growth or with W1P spaces with variable growth. Here there is a short literature. I know that there is a huge amount of contribution. I would simply to make people aware, those who aren't, because a lot of people are certainly aware of this, that there's been a lot of interest and very, very nice things can be done in this setting. And let me tell you that already the LP of X theory is quite different in some aspect from the LP theory as we know it. So there have been long time talks, for instance, how to do smooth approximation. This is possible, but not in the way we were traditionally used to think. So dealing with convolution was quite fine. Also the estimates on the maximal operator and so on. There has been a lot of work in the last decades. And let me also tell that in some sense the problems we are dealing with have already appeared in some prototypical way, for instance in image restoration, and there have been already some results on lower semi-continuity in the space of spatial functions of bounded variation, SBV, with gradient having px growth, which is here denoted by this symbol SBV P of x. So let us come closer to our setting. We will have a variable exponent, so a measurable function taking values from 1 to plus infinity, and actually we will give also this meaning to this P plus and P minus, which is quite straightforward. During the talk, we will be always assuming, and this will have a role, that P plus is strictly less than plus infinity. So we are bounded away from infinity with the exponent. And also there will be a role for P minus being strictly greater than 1. So our variable exponent is superlinear, as a gap from 1. And usually when you do with this, when you deal with this variable exponent space, you introduce this quantity, which is the modular, which is different from the norm. So they are topologically equivalent, but there is no clear relation between the modular and the norm. But I must say that for the content of this talk, you do not need to really deal with this. This is the set of functions we will be dealing with, SPV of P of x. So the functions which are special functions of bounded variation and whose approximate gradient, so the Lebesgue part of the gradient in some sense, as P of x growth, and whose discontinuity set as finite HD minus 1 measure, so bounded away from infinity. And there is the traditional notation J of U for the jump set, and U plus and U minus for the traces that SBV function takes on one and on the other side of the jump set, which is a normal neo view almost everywhere. And for technical reasons, sometimes you cannot stay in this space SBV, so you must take a larger space, this generalized GSBV P of X, which simply means that if you truncate with a C1 function, your measurable function, you end up in SBV with the growth that you have prescribed. But this is somehow the technical point. If you want to think of SBV function during the whole of this talk, it will be no problem. Basically, the results are that ones. So this is what we want to prove. So we have a functional defined on the pair function set, because you want to localize on every open set, but this is a technical point of view. So you have function defined on omega. Clearly, this is defined also on all the open subsets of omega. On this reference configuration, a variable exponent encoding the growth is given. And as I told you, this is superlinear growth, so it is always strictly bigger than 1, and it is bounded away from infinity, but it is variable. And your function meets the natural requirement that an integral functional must meet. So if you fix the function and you let the open set vary, this describes a Borel measure. Your function is lower semi-continuous. This is needed and is natural when you do gamma convergence, because your gamma limits or your relaxation will be a lower semi-continuous functional. You have a local function, a local functional, sorry. So if two functions agree on an open set, the functional also is the same, which is natural if you have integral functionals, and you prescribe the growth. So from below and from above, you postulate that your functional is controlled by a variable growth variant of the Manford-Shah functional. So from below, you have this constant alpha multiplying the gradient of u to the power P of X integrated on B plus the length of the jump set. And the same growth you also have from above, but obviously with a different constant. If not, there is nothing to prove, you have the Manford-Shah functional. And there will be an important assumption on our variable exponent that I will try to highlight during this talk. And this is a very well-known assumption to people working in variable exponent space. So for some reason, we want our variable exponent not only to be measurable, but actually to be continuous. And this you may expect, because this continuous exponent may lead to concentration phenomena. And also BV functions can have energy concentrating on some interfaces, and this interplay may be very difficult. So for a first result, you want to exclude all of these situations, so you want to have a continuous variable exponent encoding your growth. But not only you want it to have continuous, you want that the modulus of continuity is somehow prescribed. And you have this condition which is weaker than Hölder continuity. It is called Log-Hölder continuity, and says that actually your variable exponent is modulus of continuity controlled by a logarithmic function, which you only have to check for points which are close enough. That's why here 1/2, but any constant basically would do. And this condition on the variable exponent is very well known for a lot of reasons to people working in variable exponent spaces, because it allows for a lot of things which are not possible, or at least it is not clear if they are, if you drop down this assumption. And it is a condition which is very, very well suited for blow-up methods, for localization methods when you rescale, because actually the way of rephrasing, the natural way of rephrasing this Log-Hölder continuity condition is encoded in this lemma. If you take your variable exponent on a small ball, whatever the ball is, we do not prescribe the radius. You take the infimum and the supremum of the variable exponent on the ball, and you let the difference be in the exponent of the measure of the ball. This quantity, which could in principle be blowing up when the ball goes, the radius of the ball goes to 0, is instead controlled by a uniform constant. And this is actually something you are going to need when you do localization, when you do fine estimates, when you do blow-up techniques, because in some sense, when you scale, a lot of constants come into play, and there are terms which might be singular unless you have some uniform control, which this condition is going to provide. And let me tell you, this condition is very well known in the literature about LP of X or W1P of X spaces, and I will try to show in 2 or 3 words, no more than that, because it will be quite technical, why we need this. This will be probably the most technical slide I will be presenting, but just to give some flavor, just to explain, this will come. So for the moment, it must stay the message that this condition is crucial to all of our discussion. So what we want to do is to prove that such a functional is an integral representation, and we have to give a guess for the densities. So the integral functional will be composed of 2 densities, a bulk integrand and a surface integrand, in the sense that I explained before, and in some sense you have to guess what the densities might be. And when doing this, we invent nothing new. We want to resort to a very well-known machinery that says that actually the limit densities can be reconstructed by considering some local Dirichlet minimum problems. So there is something which you can always do. So you have your functional, you divide your functional on a ball by the length of the ball, you let by the measure, sorry, not by the length, or depending on the scaling. You let the radius go into 0, and you want to recover a Besicovich or Radon-Nikodym derivative. Okay, this for sure you can do, but the result is going to depend on your function u, while you want to reconstruct the density. And so in the end, the game is to show that these cell formulas, these minimum problems that you consider, can be reformulated in terms of 2 fixed competitors. So when you are on a Lebesgue point, you are essentially seeing the behavior of the optimizer for an affine function driven by the gradient of u in x0, this function which we will be denoting by L. And when you're jumping, you will be seeing essentially the behavior of a 2-valued function, which has an interface, and is jumping from a value u plus to the value u minus. So that in the end, you will be recovering a density which only depends on the position, on the gradient, or on the jump traces. So this is why we introduce these competitors, and this is actually the result one aims at proving. So I give the statement, I credit it myself and my collaborators, but I also we will be explaining that this is a very well-known machinery for problems with fixed exponent that we adapted to this situation. So in the end, what you prove is that if you have your functional, and if your functional meets your quite natural requirements, you can indeed write it as an integral functional, you can identify the densities, and the densities are in general to be identified as limits in suitable scalings, clearly 2 different scalings, the bulk, so epsilon to the power d for the bulk integrand, and d minus 1 for the surface integrants, of asymptotic problems which only depends on the position, u plus, u minus, and the normal for the second one, and on the gradient for the first one. So you have this identification, and let me also tell you that this very abstract point of view can be further specialized. So if you, for instance, have some periodic structure of on your functional, then you can recover the usual set formulas that you know for homogenization and so on. But this is very abstract and basically works for all functionals meeting some abstract requirements. Then when you know something more about your functional, you can clearly improve your results. And as I was telling you, this method is more or less known since 20 years. It was introduced at the beginning of this century, basically in some works by Bouchitté, Fonseca, Leoni, and Mascarenhas, when they were dealing with W1P or SBV spaces with constant exponent for the growth. So there is actually something new in what we did. And the proof strategy is actually always the same, also by us. And it is based on 2 asymptotic equivalencies, the ones in step 2 and in step 3. This is quite technical, but it can be understood. So in some sense, if you do nothing, you start from rough measure theory, you know that you can reconstruct the local behavior of your functional by taking minimum problems, divide by some scale, and let the parameter go into 0. But this is what you see on the left, both in step 2 and in step 3. But this is depending on your function u, and you want a representation which is clearly independent on the competitor. So the good point is coming to the right-hand side, where you show that actually these minimum problems are asymptotically equivalent to other minimum problems which take only into account the boundary conditions, because the dependence on the competitor is through the boundary condition. These are Dirichlet problems. So you can replace u with this fixed affine function on the boundary on the ball when you are in the bulk scaling, or with this jump function which is written here, which clearly jumps between the values u plus and u minus. So the crucial point when you want to prove these results is basically showing that these two kinds of problems are equivalent. For matching the boundary conditions, you need to modify your function. When you modify your functions, you can pay some energy. You want to show that the error is actually small in order to have equivalence. And so you need to prove that either your function u is very close to an affine or to a jump function, or some modification thereof is, and you have to estimate precisely the rate of convergence that you have. If not, your technique is doomed to failure. And so, as I was telling you, this is probably the most technical slide, and this is very synthetic, so it was my best effort to compress 3 pages of proof, very, very boring, in 3 lines to tell you why do we need the Lagrange continuity condition. Because we are starting from a very well-known machinery. So we know exactly what we have to do. We know the construction that have to be somehow performed. And the crucial point, this is for instance step 3. For step 2 you have similar difficulties, but it is a little bit lighter. The crucial point is getting these rate of convergence estimates. So when you blow up your energy around the discontinuity point, you know that your function u is close to a two-valued function, jumping from u plus to u minus across any interface. But this is not enough. What you have to prove is that you can modify a little bit your function by keeping the boundary data, but having a very, very good rate of convergence in the P of x. I would be tempted to say in the P of x norm. This is not the P of x norm, it's the modular, but it is in some sense equivalent. And the point is, why are you going to need the Lagrange continuity condition? Because if you perform the usual construction, you need to have fixed exponents. Fixed exponents that may vary with the ball. So you can, for instance, take the infimum over the ball of radius epsilon of the variable exponent, perform the Bouchitté-Fonseca construction. You get an estimate, but this is not enough, because at exponent you have P epsilon minus, and you want to get to P epsilon of x. Then you can do some improvement by using some Poincaré inequality, because you have some control on the gradient, and this you like. But Poincaré inequalities have some scaling. They scale in some way with the domain, and then you have some powers, some mismatch between P of x and P epsilon minus. And the Lagrange continuity condition is exactly the one that tells you, it's sufficient, I do not know if it is necessary, but it looks very close to be optimal, that the constants that arise, the Poincaré constants that arise with the exponent which you have to put actually stay bounded. So this is a general point where you are going to need some condition on your variable exponent, and otherwise your result cannot be proved. So, as I told you, there are some applications. How much time do I have? 60 minutes. This will be more than enough. So, the first natural application of this integral representation result is when you deal with gamma convergence. So this is our setting. Now we have these local functionals. Here it's written one functional, but actually you must imagine a sequence of functional, all satisfying the same conditions, which are standard in the literature up to the fact that we are introducing a variable exponent growth on the bulk integrand. And so these assumptions are more or less standard. There is something on the condition G2, but I do not really want to bore you with this. So if you can also imagine densities, for instance, that are only depending on the position and on the normal to the jump set, which will be classical, and you do not have to worry about the condition G2. You take a sequence, because if, for instance, you want to do homogenization, it's a possibility, or you want to take into account any kind of asymptotic effects. And the first goal when you do gamma limits is to prove that if you have a sequence of functional all meeting these requirements uniformly with uniform constants, this must be for sure, then your limit functional is again of this kind. And this is why you need an integral representation result, because actually what you do is usually to show that the abstract requirements are met, and then you can invoke the integral representation result to conclude the argument. And this is the result that one can indeed prove. So if you take a sequence of functions of this kind and you consider the convergence in measure, or if you had some lower order perturbation, you could even consider LP topology, whatever. This is not the core of the matter. You actually can show that your functionals gamma converge to a functional of the same kind, and as I told you, you have also some expression, some asymptotic formula that allows you, at least abstractly, to reconstruct the limit densities coming into play. But in this slide, there is a somehow deceiving title. So this is a gamma convergence result. It's nice, use integral representation, yet some technical difficulties, so you must be happy with that. But this is not completely satisfactory. This is not completely satisfactory because in the end, one has not to forget that you want to provide abstract results which, however, meet some application or are likely to meet some of them. So you want that actually your asymptotic densities can be actually computed if one is really willing to, or in need of doing this. And actually there is one effect that we can also account for, and this comes later. This proof is not interesting, at least today. So this separation of scale effect, this is something which is very well known in the fixed exponent setting, and our goal was to generalize this to the variable exponent setting. And this has really to do with superlinearity of the exponent. So let us suppose for a moment that p of x is actually fixed. So it is a fixed exponent p. If you want to think that it is 2 for these 2 minutes, you can make it. Then you know that actually you have this gamma limit, which is an integral function, but actually you also have a decoupling effect. So if you want to recover the bulk density, you can really restrict your functional to Sobolev functions, do gamma convergence in this more regular setting, recover recover the asymptotic density, which can be very easy, for instance, if you do relaxation, because in Sobolev setting, you know that you have explicit formula for relaxation via, for example, quasi-convexification or so on. And you have recovered the bulk density. While for the surface density, you can restrict your functional to piecewise constant functions, so forget gradients, simply having functions with a finite number of values in their image, and do gamma convergence in that setting. So having more or less a purely interfacial problem. You do gamma convergence in that simplified setting, and you get the surface density. So when you have a fixed growth, which is superlinear, what you know is that actually this problem is coupled, but the limit densities can be decoupled when you want to recover them, but actually for the minimization effects, they will be again put together. But this helps the computation. And actually, this is what we also want to prove in this setting under some assumptions. Again, they are basically the same. They all is slight difference. You have a modulus of continuity for the integrand f, but nothing bad, and you have a p of x growth. So what we want to prove is claimed here. There is no interaction in the sense of how to compute them, because clearly for the limit function they interact, but for the way of computing there is no interaction between the asymptotic bar density and the surface density, and you want to use superlinearity of the exponent. And this is the result that I claimed. This goes back to the setting by Cauchy-Mucci, which will be adapted to our setting. So the starting point is I restrict my functional to regular functions. By regular, I mean Sobolev functions. So I do not see any jump. And it is well known there is this result that actually the functional is gamma converging in W1P of x to some limit functional. And this is the result by Cauchy-Mucci. When we come to our setting, we have fracture. So our functions are in a way weaker space, which is GSBV. So they will have a jump set, but still the good point is that the limit density is the same. It's the same one that you recover by doing gamma convergence in the Sobolev setting. And probably this is the last thing that I want to tell you. This is again a part of the story where log-Elder continuity of the growth exponent is going to play a very important role. Because what you do is clearly you want to show that your asymptotic formula is not seeing the jump. So you do a blow up and you want to show that actually the competitors for the limit minimum problem, which have small jump sets, this is simply localization and gamma convergence, you are close to a Lebesgue point of the limit energy. So jump is not contributing to the energy there. So you do some rescaling, you do some blow up. In general, you know that you have these minimum problems in GSBV or SBV, whatever, but these competitors have small jumps, and you want to substitute them with Sobolev functions, because you say, okay, if the jump is not too large, probably you can modify the function, not seeing it, and have asymptotically the same energy. And there is a way of doing this. There is the class, there are a lot, but the way of doing this is based on Lipschitz approximation. For instance, one possibility is using some losing type argument, plus you also need some biting convergence, because first you produce some Lipschitz function with bounded gradients in some Lebesgue norm, and then you want also to show that actually this power is equi-integrable, so you need biting, but this is the crucial point is losing. The rest comes. And again, this can be done with a fixed exponent. Or you can have an exponent which is fixed on every ball. So you can parameter vary. Like for instance, take p epsilon minus on each ball, and you can have a losing approximant with good decay properties on the gradient to the power p epsilon minus. But again, you want p of x in the exponent, non p epsilon minus, and you need some log-Elder continuity. And there is an additional difficulty. It's actually, when you do this losing construction, you have obviously a Lipschitz constant which is increasing, which is going to explode, because in the limit your approximant is not, your function is not Lipschitz anymore. The good point is that actually you can choose the rate where this Lipschitz constant is exploiting. You can choose in a way which is comparable to the size of the ball. This is the core of the argument. And once you can do this, you can repeat the argument I was telling before. You have some scaling, you know how it scales with the measure of the set, and you have some control on the exponent that keeps some constants bounded. So this can be done. This is not interesting. This is interesting. So it's really the last thing I wanted to tell you. So this was the beginning. So it started a bit like maybe we didn't know exactly what to do, so we thought these problems are interesting, let's try to explore them and see what happens. And the variable exponent setting is the one where you can really do most of the things really with the hands. So you take the known arguments, you modify them a bit, you perform construction, but as I told you, variable exponent is only one part of non-standard growth for the bulk energies. This is a very well explored issue in a Sobolev setting. When it's coupled with free discontinuities, not that much is known. And actually we went a little bit farther on this direction with Stefano and Dario by exploring in a more general way the issue of lower semi-continuity and relaxation via integral representation for bulk energies with non-standard growth, and this is a preprint which we recently issued. And if you want to take a more general perspective, which also encompasses the variable exponent, then you are really going to need Orlich spaces, generalized Orlich spaces, estimates on the maximal operator, and a lot of techniques which are very well known to the experts of the setting. There is also a case of which I have, there are a lot of cases of which I actually have no clue, because basically we only did the positive direction. So we explored what is complying very well with the blow-up techniques that we know. But non-standard growth is only one part of the world. You can, for instance, also consider the case of mixed growth, which is very natural when, for instance, you have polyconvex energies. So if you split them in a gradient energy, for instance, also power energy on the gradient, plus something depending on the determinant of the deformation, then you end up with mixed growth. In the Sobolev setting, it is known when the relaxation gives rise to an integral function. It is also known when there is some gap and how to characterize it. There is a huge literature. There is nothing in our setting, and there are some non-trivial. This is actually what I cannot even imagine, because all these results basically rely on the fact that the determinant of the strain, when you are in a Sobolev setting, is the Jacobian. It has a distributional meaning, and you have change of variable formula, and you have a lot of interesting stuff. When you are in a BV setting, you really point-wise have the determinant of an approximate gradient. And this can be any function. It has no structure, the curve can be way different from zero, can be whatever. And so the arguments of Fonseca, Mali, and Fusco-Hutchinson, for instance, that gave some results in the Sobolev setting, are for sure not to be directly reproduced in this setting. I expect that some gap may be appearing, but I have no idea of how it can be characterized. So probably some direction for those who are interested to be explored. And I have been a little bit longer than expected, so this is the content of this talk, and let me thank you for your attention.